Welcome! In this session, we'll explore problem number 142, titled Linked List Cycle 2. This is a fascinating problem that dives into linked list operations and requires efficient cycle detection. Let's break it down step by step and uncover the optimal solution. In this problem, we are given the head of a linked list, and our goal is to determine if there is a cycle in the list. If a cycle exists, we need to return the node where the cycle begins. If no cycle is present, we simply return null. A cycle in a linked list occurs when a node points back to a previous node in the list, creating a loop. The variable POS is used internally to denote the index of the node where the tail connects, but it is important to note that this value is not provided as an input parameter. Additionally, the problem specifies that we must not modify the given linked list. The input is represented by the head node of the linked list, and the output is either the starting node of the cycle or null, depending on whether a cycle exists. As an example, consider a linked list with values 3, 2, 0, -4, and POS equal to 1. This means the tail of the list connects to the second node, which has a value of 2. If we visualize this, the list starts at 3, moves to 2, then to 0, and finally to -4 before looping back to the node with value 2. This creates a cycle in the list. Since the cycle begins at the node with value 2, that node is the output. Another example is a linked list with values 1, 2, and POS equal to 0. Here, the tail connects back to the first node, which has a value of 1. Visually, the list starts at 1, moves to 2, and then loops back to 1, forming a cycle. In this case, the node where the cycle begins is the first node, so the output is the node with value 1. In contrast, if we have a linked list with a single node, such as 1, and POS is -1, it means there is no cycle in the list. The node simply points to null, and there is no connection back to any previous node. Graphically, the list only contains the single node with value 1, and since no cycle exists, the output for this case is null. Now let's consider some edge cases. If the linked list is empty, meaning the head is null, then there is no cycle, and we return null. For a single node list without a cycle, the result is also null. However, if there is only one node and it forms a cycle by pointing to itself, the output will be that single node. Similarly, a larger list without any cycle will result in null, while a list where the cycle begins at the first node will require us to identify and return that starting node. These constraints ensure we handle all possible scenarios while maintaining O(n) time complexity and O(1) space complexity without modifying the linked list. To solve the problem of detecting a cycle in a linked list, one approach we can consider is the brute force method. The intuition behind this approach is straightforward. As we traverse the list, we use a hash set to keep track of all the nodes we've visited. If we encounter a node that's already in the set, we know we've found the start of the cycle. On the other hand, if we reach the end of the list, which is represented by a null pointer, we can conclude that there is no cycle. While this method is simple to implement, it has limitations, particularly because it requires additional memory to store all the visited nodes. Here's a Python implementation of this brute force approach, where we use a set to track visited nodes and return the node where the cycle begins if one exists. Analyzing this brute force approach, we observe that its time complexity is O(n) as we traverse each node in the linked list once. However, the space complexity is also O(n), as we need to store all visited nodes in a hash set. While this method is conceptually simple, its reliance on extra memory for storage makes it less than ideal for larger linked lists. To address this inefficiency, we turn to a more optimized solution, Floyd's cycle detection algorithm, also known as the two-pointer approach. The intuition here is to use two pointers, a slow pointer and a fast pointer, moving at different speeds. If there is a cycle, these two pointers will eventually meet. Once they do, we can use a mathematical property of the cycle to determine its starting point. This approach eliminates the need for extra memory, making it much more space efficient. Here's how Floyd's algorithm works in detail. First, both the slow and fast pointers start at the head of the linked list. The slow pointer moves one step at a time, while the fast pointer moves 2 steps. If the fast pointer reaches the end of the list, meaning it encounters null, there is no cycle. However, if the slow and fast pointers meet, we've confirmed the existence of a cycle. At this point, we reposition one of the pointers back to the head of the list while leaving the other at the meeting point. Both pointers then move one step at a time. The point at which they meet again is the start of the cycle. This method is incredibly efficient, with a time complexity of O(n) and a space complexity of O(1), as it requires no additional storage. The use of the cycle's mathematical properties is what makes it both elegant and optimal. Given the options, the chosen strategy for solving this problem is Floyd's cycle detection algorithm. This approach stands out because of its efficiency, achieving O(n) time complexity and O(1) space complexity. Unlike the brute force method, it doesn't require additional data structures, such as hash sets, to track visited nodes. This makes it highly practical for large linked lists. One of the key insights of this algorithm, often referred to as the aha moment, is the realization that the meeting point of the two pointers can be used to locate the start of the cycle. This is based on the mathematical property that the distance from the head of the list to the start of the cycle is equal to the distance from the meeting point to the start of the cycle. By leveraging this property, Floyd's algorithm provides a simple yet powerful solution to the problem. However, it's worth noting that while Floyd's algorithm is optimal, its implementation may be less intuitive for beginners due to the reliance on the mathematical properties of the cycle. On the other hand, the brute force approach, despite being easier to understand, is not scalable for larger linked lists due to its significant space requirements. In conclusion, Floyd's cycle detection algorithm is the best solution for this problem. It strikes the ideal balance between efficiency and clarity, offering a deterministic and reliable method for cycle detection with minimal trade-offs. While it may require a bit more effort to understand it first, its elegance and optimal performance make it the clear choice for solving this problem in practice. In this problem, we are tasked with determining whether a given linked list contains a cycle. If a cycle exists, we need to identify the node at which the cycle begins. Otherwise, we return null. To achieve this, we'll start by exploring the brute force approach, which leverages a hash set to detect cycles efficiently. First, we initialize an empty hash set called visited_nodes. This data structure will keep track of all the nodes we encounter during our traversal, allowing us to detect duplicates in constant time. Next, we use a pointer, current, to traverse the linked list node by node, starting from the head. For every node visited, we check if the node's reference already exists in the hash set. If it does, it means we've revisited the node, confirming the presence of a cycle. At this point, we return the current node as the starting point of the cycle. If the node reference does not exist in the hash set, we add it to the set and move the current pointer to the next node in the list. The traversal continues until either a cycle is detected or the end of the list is reached. If we reach the end of the linked list, or current becomes null, we conclude that no cycle exists and return null. Key insights about this approach include the use of a hash set, which is integral to detecting cycles efficiently. By storing node references, we can quickly check for revisits in constant time. This algorithm cleverly leverages the fact that a cycle in a linked list guarantees that revisiting a node is unavoidable. The termination conditions are straightforward. The algorithm halts as soon as a cycle is detected or when the traversal reaches the end of the list. This ensures that the approach is both simple and effective. To implement this approach, we use two primary data structures. First, the hash set, visited_nodes, is used to store references of all visited nodes. This choice is deliberate because the hash set's average time complexity for insertions and lookups is constant, or O(1), making it efficient for tracking nodes during traversal. Second, a single pointer, current, is used to traverse the linked list node by node. The computational complexity of this algorithm is also worth noting. In terms of time complexity, each node in the linked list is visited exactly once, and each hash set operation, whether an insertion or a lookup, takes O(1) on average. As a result, the overall time complexity is O(n), where n is the number of nodes in the list. For space complexity, the hash set stores references to nodes, with its size capped at n, which occurs if no cycle exists. Therefore, the space complexity is O(n). Special edge cases to consider include an empty list, where the head is null, and a single node list without a cycle, where we immediately return null. Another edge case to consider is a single node list where the node's next pointer points back to itself, forming a cycle. In this scenario, the algorithm should correctly detect the cycle and return the single node. For linked lists with multiple nodes but no cycle, the algorithm should traverse the entire list and return null after confirming that no node is revisited. Finally, in cases where the linked list contains multiple nodes and a cycle, the algorithm should detect the cycle and accurately identify the starting node of the cycle. Let's walk through an example to understand this better. Imagine we have a linked list represented as 1 2 3 4 5 3, where the cycle starts at node 3. We begin by initializing the visited underscore node set as empty. Starting at node 1, we add it to the set and move to the next node. At node 2, we add it to the set as well and proceed to node 3. We continue this process for nodes 3 and 4, adding each to the set as we go. At node 5, we include it in the visited underscore node set and then move to the next node, which takes us back to node 3. At this point, the algorithm checks the hash set and finds that node 3 already exists in visited underscore nodes. This confirms the presence of a cycle, and the algorithm returns node 3 as the starting point of the cycle. To better understand how this is implemented in code, take a look at the Python solution provided. We define a list node class to represent nodes in the linked list. The detect underscore cycle function begins by initializing an empty hash set called visited underscore nodes and a pointer, current, set to the head of the list. The while loop iterates through the list as long as current is not null. If the hash set contains the current node, we return it as the starting point of the cycle. Otherwise, the node is added to the hash set, and current is advanced to the next node. If the loop terminates without detecting a cycle, the function returns null, indicating no cycle is present. In conclusion, the brute force approach offers a straightforward solution to the linked list cycle detection problem. While it is not the most space-efficient method due to its space complexity, it is intuitive and easy to implement. This makes it particularly suitable for beginners learning about linked lists and cycle detection. By leveraging a hash set, the algorithm efficiently tracks visited nodes, ensuring that cycles are detected in time. This approach also provides a solid foundation for understanding more advanced techniques that solve the problem with reduced space complexity. Overall, it is a valuable starting point for tackling cycle detection problems in linked lists. To implement the solution for detecting the start of a cycle in a linked list, we first define a basic structure for a linked list node using the listNode class. This includes an initializer method to set the value of the node and a reference to the next node, which starts as none. Next, we define the detectCycle method within the solution class. This method begins by initializing two pointers, slow and fast, both starting at the head of the linked list. The first step is to determine if a cycle exists. To do this, we use a while loop that continues as long as the fast pointer and its next reference are not none. Inside the loop, the slow pointer moves one step at a time, while the fast pointer moves two steps. If there is a cycle, the slow and fast pointers will eventually meet at some point within the loop. However, if the loop exits without the pointers meeting, it means no cycle exists, and we return none. Once we establish that a cycle exists, the second step is to locate the exact node where the cycle begins. For this, we reset the slow pointer back to the head of the list, while the fast pointer remains at the meeting point. Then, we proceed to the next phase of the algorithm. At this stage, both slow and fast pointers move one step at a time through the list. This continues until the two pointers meet again. The key observation here is that the meeting point will be the node where the cycle begins. Once the pointers converge, we return the slow pointer, which now points to the start of the cycle. This completes our implementation. The algorithm efficiently detects and locates the start of the cycle in the linked list using only two pointers in constant space, making it an optimal solution for this problem. In this Java implementation, we first define our listNode class, which represents a node in a singly linked list. Each node stores an integer value and a reference to the next node in the list. The primary method here is detectCycle, which takes the head of the linked list as input and determines if there's a cycle. If no cycle exists, it returns null. Now, the first step in this process is to detect whether a cycle exists at all. We use two pointers for this purpose, slow and fast. Both pointers start at the head of the list. The slow pointer moves one step at a time, while the fast pointer moves two steps at a time. As the loop runs, we check if the fast pointer or its next reference becomes null, which would mean there's no cycle. However, if the slow and fast pointers meet at some point, it confirms the presence of a cycle, and we exit the loop. Once the presence of a cycle is confirmed, the next step is to locate the exact node where the cycle begins. If the fast pointer or its next reference is null at this stage, we return null because no cycle exists. Otherwise, we reset the slow pointer to the head of the list, while the fast pointer remains where the cycle was detected. Both pointers now move one step at a time. The point where they meet again is the start of the cycle. This works because both pointers are effectively traveling the same distance, one from the head and the other from the meeting point, which leads them to converge at the cycle's starting node. Finally, we return the slow pointer, which now points to the beginning of the cycle. To solve the problem of detecting the start of a cycle in a linked list, let's begin with an example where a cycle exists. Here, the linked list contains nodes with values 1 through 5, and the last node points back to node 3, forming a cycle. We initialize two pointers, slow and fast, both starting at the head of the list, which is the node with value 1. In the first step, we move slow one step forward and fast 2 steps forward in each iteration. Initially, both pointers are at node 1. In the first iteration, slow moves to node 2, and fast moves 2 steps ahead to node 3. During the second iteration, slow advances to node 3, while fast moves from node 3 to node 5. This process continues until the two pointers meet, indicating a cycle is present. In the third iteration of the cycle detection phase, slow moves to node 4, and fast also moves to node 4. At this point, slow equals fast, confirming the presence of a cycle. Now, to identify the starting node of the cycle, we reset the slow pointer to the head of the list, which is node 1, while keeping fast at the meeting point, which is node 4. Both pointers are then moved one step at a time. In the first iteration of this phase, slow moves to node 2, and fast advances to node 5. In the second iteration, slow progresses to node 3, and fast also moves to node 3. When the two pointers meet again, they are at node 3, which is the start of the cycle. Thus, the output for this example is the node with value 3. Now, let's consider an example where the linked list does not have a cycle. The list contains nodes with values 1 through 5, and the last node points to null. We start by initializing the slow and fast pointers at the head of the list, which is the node with value 1. Just like before, we move slow one step forward and fast 2 steps forward in each iteration. In the first iteration, slow moves to node 2, and fast moves to node 3. In the second iteration, slow advances to node 3, and fast progresses to node 5. In the third iteration, slow moves to node 4, while fast attempts to move 2 steps but reaches the end of the list, becoming null. Since the fast pointer reaches the end of the list without meeting the slow pointer, we conclude that no cycle exists. The output for this example is none. Next, let's analyze a special case where the linked list consists of a single node that forms a cycle by pointing to itself. The input here is a single node with value 1, and its next pointer refers back to itself. As usual, we initialize slow and fast at the head of the list, which is the node with value 1. In the first step of the cycle detection phase, we move slow one step forward and fast 2 steps forward. Since the node points to itself, both slow and fast remain at the same node. At this point, slow equals fast, confirming the presence of a cycle in the list. Once the cycle is detected, we proceed to find the starting node of the cycle. We reset the slow pointer to the head of the list, which is still the node with value 1, while keeping fast at the meeting point, which is also the same node. We then move both pointers one step at a time. Since the node points to itself, both slow and fast remain at the same node in the first iteration. With both pointers meeting at the node with value 1, we determine that this node is the start of the cycle. The output for this example is the node with value 1. To analyze the time complexity, our solution involves two distinct steps. First, we check if a cycle exists in the linked list. Here, we use two pointers, the slow pointer, which moves one step at a time, and the fast pointer, which moves 2 steps at a time. If there is no cycle, the fast pointer will eventually reach the end of the list after traversing all the nodes, which takes n time, where n is the number of nodes in the list. However, if a cycle is present, the fast pointer will catch up to the slow pointer within the cycle. This also takes n time because the fast pointer gains one step on the slow pointer per iteration, and at most the entire cycle length needs to be covered for them to meet. Once a cycle is detected, the second step begins, finding the starting node of the cycle. Here, we reset the slow pointer to the head of the linked list and move both slow and fast pointers one step at a time. They will meet at the cycle's starting node. This traversal involves covering the non-cyclic part of the list, if any, and one traversal of the cycle, which also takes n time. Thus, each step is linear in complexity, making the detection and starting node identification efficient. Now, let's summarize the overall time complexity. Step 1, detecting if a cycle exists, has a time complexity of n. Step 2, finding the starting node of the cycle, also takes n. Adding these together, the total time complexity becomes n plus n, which simplifies to n. Next, we consider the space complexity. The algorithm uses two pointers, slow and fast, and these require a constant amount of memory regardless of the size of the input. No additional data structures are utilized, such as hash maps or arrays, to store information. As a result, the space complexity of this algorithm is 1, which is optimal because we only use a fixed amount of space during the execution of the solution. When comparing this approach to a brute force method, the advantages of the optimized solution become clear. A straightforward way to detect a cycle could involve using a hash set to store all the nodes visited during the traversal. If a node is encountered that is already in the hash set, we know a cycle exists. While this method works, its space complexity is n, as we may need to store all n nodes in the hash set in the worst case. The time complexity remains n, since we still traverse the list once. In contrast, the optimized two-pointer approach, also known as Floyd's cycle detection algorithm, achieves the same linear time complexity of n, but crucially improves the space complexity to 1, by not using any additional memory to track visited nodes. This makes the optimized approach significantly better in terms of memory efficiency, especially when working with large linked lists. To further understand why the time complexity of the two-pointer approach is n, we can look at the mathematical reasoning. In the first step, the fast pointer moves at twice the speed of the slow pointer. If a cycle exists, the distance between the two pointers decreases by 1 in every iteration because the fast pointer gains a step on the slow pointer. The maximum distance they need to cover is proportional to the length of the cycle, so they will meet within n steps. In the second step, once a cycle is detected, finding the starting node involves each pointer moving at most n steps, which includes traversing the non-cyclic part of the list and the cycle itself. This ensures that the total time complexity remains n. Overall, the optimized solution is both time-efficient and space-efficient, making it a robust choice for solving the linked list cycle problem compared to the brute force method. When working on linked list problems, it's important to be mindful of common mistakes. For example, not accounting for edge cases can lead to serious issues. If you fail to handle scenarios like an empty input, a single element list, or a cycle that starts at the head, your solution might crash or run indefinitely. Another common error is modifying the data structure prematurely, such as reversing nodes before solving the problem. This can corrupt the linked list, especially if the problem requires you to return it to its original form. Efficiency is also key. Unnecessarily using a hash set when a slow and fast pointer approach would suffice leads to wasted space. Finally, incorrect cycle detection logic, like assuming one traversal is enough to definitively detect a cycle, can cause false positives or negatives. Using a reliable method like Floyd's algorithm avoids these pitfalls. Now, overlooking constraints can also trip you up. For instance, assuming all nodes in the linked list are distinct or not considering negative values in node properties might lead to an incomplete solution. In terms of insights, Floyd's tortoise and hare algorithm is a must-know technique for cycle detection. It's highly efficient, operating in n time and 1 space, which is optimal. When solving linked list problems, always think about edge cases, such as null inputs, single-node lists, or circular references. These often come up in interviews. Additionally, while hashing can simplify some problems, it's worth evaluating whether a two-pointer approach or a mathematical method can achieve the same result with less space overhead. Finally, be ready to discuss trade-offs, like highlighting that although the hash set approach is simpler to implement, it's less memory efficient compared to Floyd's algorithm. There are also related problems that you should be aware of, as they often build on similar concepts. For instance, LeetCode 141, linked list cycle, focuses on simply detecting whether a linked list contains a cycle. LeetCode 142, linked list cycle 2, which we're discussing here, takes it a step further by asking you to identify the starting node of the cycle. LeetCode 160, intersection of two linked lists, is another common problem where you need to find the node where two linked lists intersect. Finally, LeetCode 876, middle of the linked list, introduces the slow and fast pointer technique to determine the middle node of a list. Familiarity with these problems will not only improve your understanding of linked lists but also help you recognize patterns in interview questions. There are multiple approaches to solving cycle detection problems, each with its own trade-offs. A brute force method involves using a hash set to store visited nodes as you traverse the list. If you revisit a node, it means there's a cycle. While simple to implement, this approach uses O(n) space. Alternatively, Floyd's tortoise and hare algorithm is optimal in both time and space. It runs in O(n) time and uses O(1) space by employing two pointers moving at different speeds. However, it can be slightly harder to understand and implement. Another option is modifying the node structure by marking visited nodes, for instance, with a visited flag. This saves space but isn't ideal if the linked list must remain unaltered. Lastly, recursive detection can track visited nodes but comes with the risk of a stack overflow for large lists. Each approach has its pros and cons, so it's important to choose based on the problem constraints and requirements. Great job! We've successfully solved problem number 142, linked list cycle 2. This problem highlighted the importance of efficient algorithms like Floyd's cycle detection. Remember to practice similar problems to master these techniques. If you enjoyed this session, don't forget to like and subscribe. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!